Hi there, welcome back to the channel, and in today's video I'll be showing you how to calculate the equivalent capacitance of capacitors connected in series or parallel. So to start off the video, I'll just be elaborating on these formulas on the screen that you can see right now. Initially, those formulas may be a bit confusing to look at, but I promise you it's not so difficult. So if you were to sum up a series connection of capacitors, you would sum them up the same way you would a parallel resistor connection. Now, if you're not too familiar with what I mean by that, I recommend you watch my first video on this channel where I further discuss series and parallel resistor connections and circuit problems. And for the parallel capacitor connection, you would sum them up the same way you would for a series resistance connection, like this. And that's all you need to know about summing them up, series and parallel capacitors. But there's also another thing you should be aware of when dealing with these types of problems. Capacitors, they're measured in farads, such as this. This capacitor has 10 microfarad. Now, what do I mean by micro? Micro is a prefix to the unit, and what that is short for is times 10 to the minus 6. So what this really is up here is 10 times 10 to the minus 6 farads. And you can also get nanofarads, that means times 10 to the minus 9, and also pico, which is times 10 to the minus 12. And they are all the most common ways in which capacitances can be measured and shown to you in whatever situation you're in. So I think this covers a lot of what you need to know about the basics of capacitors. So let's solve some problems and put this theory to the test. So for the first problem, what I want you to do for this circuit is to just calculate the equivalent capacitance in this circuit. Ignore the voltage source. All I want you to do is to calculate the equivalent capacitance. Take your time if you need to and pause the video to work on the solution. So to start off with this problem, let's sum up the capacitances in the way that I showed you to previously. So 1 over 0.1 times 10 to the minus 9 plus 1 over 100 times 10 to the minus 6, and raise this all to the power of minus 1 in a bracket, and your answer should be equal to around 100 picofarad. That's the answer to problem 1. For this problem 2 here, what I want you to do is the same thing. Ignore the voltage source V1 and focus on C1 and C2 to calculate the equivalent total capacitance in this circuit. Take your time if you need to and pause the video to work on the solution. So calling on from the previous formula discussed, we can just sum this up very simply, but take note that milli, the small m here, is essentially times 10 to the minus 3. So it's very important when we enter this on the solution in the calculator. So we just have here 10 times 10 to the minus 6, that's C1, and for C2 it's 0.1 times 10 to the minus 3, which will give us an answer of 110 microfarad. That's your answer for the equivalent capacitance of this circuit for problem 2. And for this problem, once again, what I want you to do is to ignore the voltage source V1 and just focus on calculating the equivalent capacitance in the circuit. And so take your time if you need to, and pause the video to work on the solution. So the first step to tackling this problem is to calculate the equivalent capacitance of C3 and C4. So again, you would tackle this the same way you would a parallel resistor connection. 0.1 times 10 to the minus 12 plus 1 over 100 times 10 to the minus 6. I raise that all to the power of minus 1, and we get around 100 femtofarad. Now femto is times 10 to the minus 15, just so you are aware. Again, any equivalent to this value should work, but this is just the value I'm using in this solution here. So then this equivalent capacitance is now in parallel with C2, 0.1 microfarad. So we just add it in this way. Let's say 100 here. What am I doing? And this is equal to 0.1 microfarad basically, because that 100 femtofarad is very small, so it's pretty much negligible. But now we have this 0.1 microfarad in series with the C1 50 microfarad. So the final thing to do here is 1 over 50 times 10 to the minus 6 plus 1 over 0.1 times 10 to the minus 6. Raise that all to the minus 1. And our final answer is around 100 nanofarad. And that's your final answer for the equivalent capacitance of this circuit. So that's all I have for today's video. Thank you very much for watching, and I hope you enjoyed. But just before this video ends, I'd just like to make a brief announcement for my other channel that you can now find in the homepage of this channel, and it's called Team Golf 2024. This channel documents the progress of my micromouse, where I work with a team to assemble a micromouse, which is essentially a robot with 2 wheels pretty much, and we make it do certain tasks such as obstacle avoidance, and currently we are working on white line following. So it's just a bit of a nice channel there to show you the practical side of all this theory I teach on this channel, just for your information. So yeah, thank you again very much for watching this video.